When you write a simple assignment like x equals 5, Python most physically store that data. This diagram pulls back the curtain on that process, dissolving the syntax into a grid of raw memory addresses on your machine. Everything in Python eventually becomes bytes stored somewhere in physical RAM. You have likely heard the phrase, "everything is an object in Python." While true, it is an incomplete mental model. Knowing that a number is an object does not explain how the interpreter actually structures and retrieves that data when your code runs. To write highly efficient Python, you need to stop imagining variables as boxes that hold data. Instead, you need to visualize your code as a physical runtime graph of isolated objects connected by a web of memory pointers. We are going to rebuild Python's architecture from the metal up. We will track how bytes in physical RAM are organized into CPython heap structures, and then see how those structures are puppeted by execution frames. Grasping this physical layout is the exact threshold where a developer stops guessing how Python behaves and starts engineering systems that leverage its internal logic. This diagram shows a contiguous block of abstract hex memory, representing the heap. The heap is the physical memory space where the Python runtime allocates space for its objects. Here, a single chunk illuminates to store the integer 5, wrapped inside a structure called a pylong object. Every single piece of data in Python is prepended by a universal C-struct. As the object expands vertically, we see the PyObject header sitting at the top. It requires two strict slots, a reference count and a type pointer. These sit directly above the actual integer data. The ref count, or reference count, tracks exactly how many active variables currently point to this specific memory block. Here it displays the number 1. When this count hits 0, Python triggers garbage collection, the automated process of freeing memory when data is no longer needed. The second slot is the type pointer. This is a memory address that draws a line outward, linking this raw chunk of data to its actual behavioral definition located elsewhere in RAM. The actual value, the integer 5, sits at the absolute bottom of this structure. It cannot exist on its own. Its identity relies entirely on the header above it. Data in Python is never naked. It is perpetually encapsulated by the PyObject header, so the runtime graph can continuously track and manipulate it. Following that type pointer through memory, it arrives at a newly rendered block, the PyType object. In Python, types like integer, list, or dictionary are not abstract rules written in the compiler. They are physical objects occupying specific RAM addresses, constructed exactly like the data objects we just examined. Looking inside the type object, we find its internal fields. The tpdict field highlights here, storing a pointer that leads directly to a completely separate dictionary object. This dictionary dictates what the integer can do. It visually links a string key, like the addition method, to a specific Py method descriptor. A descriptor is simply an object that manages attribute access and points to the underlying C function that executes the math. When you look up an attribute, Python is simply traversing these exact pointer chains through dictionaries and RAM. Method calls execute the exact same mechanical graph traversal. Look up the string key, follow the pointer, execute the function. This physical structure is how dynamic typing operates. Behavior isn't fixed, it is merely a web of mutable pointers. Because an object's behavior is dictated by connected dictionaries, techniques like monkey patching, the dynamic modification of a class at runtime, are structurally identical to updating any standard dictionary key. Consider a basic assignment. You set the variable a to 10, and then you set the variable b equal to a. This diagram shows the traditional mental model of variables, distinct boxes storing independent copies of the number 10. This is entirely incorrect in Python. Python uses namespaces. As this table shows, variables exist strictly as string keys within isolated dictionary structures. The keys a and b drop pointer arrows that converge onto one single shared object in the heap. When you type b equals a, Python copies 0 data. It generates a new dictionary key named b and points it to the exact same memory address a is looking at. If you apply this to a mutable object, like a list, the mechanics become highly visible. If a and b point to the same list and you append an item to b, Both dictionary keys observe the exact same underlying memory object expanding in the heap. Frustrating bugs like accidentally mutating default arguments across multiple function calls happen because developers expect variables to act as isolated storage boxes rather than acknowledging the namespace to heap pointer map. To manage this massive web of pointers and namespace dictionaries, Python relies on a strict execution architecture based on stack frames. Every time a function is called, a PyFrame object is generated. On the left side of the split screen, the active frame expands to show its internal local stick and evaluation stack, while the right side tracks the heap. The frame resolves variables using the LEGB rule, local, enclosing, global, built-in. This highlight box physically traces that path, checking the local dictionary first, falling back to the global dictionary, and finally the built-in dictionary, until it finds a matching string key. Once the variables are located, the actual computation occurs inside the frame's evaluation stack. Python compiles your text into bytecode, the low-level instruction set the interpreter actually executes. Bytecode instructions like load fast or binary add execute by literally pushing and popping object pointers onto this evaluation stack. An instruction pointer continuously ticks downward, tracking exactly which bytecode operation is currently manipulating those memory addresses. Executing code is a mechanical process. A frame pushes object pointers onto a stack, evaluates them against type dictionaries, and stores the resulting pointers back into a namespace. Stepping back, this hero visual maps the complete Python runtime architecture operating as a single unified system. It is built on 3 pillars: the namespace dictionaries holding your variable labels on the left, the densely interconnected data objects in the heap on the right, and the stack frames orchestrating the execution. This graph reveals exactly how Python passes arguments. Notice how a variable inside one frame duplicates its pointer arrow, handing it to a newly generated key in a second frame. Both point to the exact same heap object. This is pass by object reference. Functions only ever receive references to objects. They never receive independent copies of the data. Saying everything is an object sounds simple. The physical reality of the CPython graph is a highly structured, complex network of exact memory addresses, mapping attributes to actions. By visualizing this exact namespace to heap pointer architecture, Python's most opaque behaviors stop being confusing quirks. They become strictly logical, mathematically predictable systems operations.